Okay, let's talk through this question with the bug. So, the common misconception here is because the bug was obliterated, we like to think that the force of the windshield on the bug is greater than the force of the bug on the windshield, but that is not the case. They are equal and opposite to one another. Okay, so that would be our action-reaction pair. There, the force of the bug on the windshield, the force of the windshield on the bug, they're equal force, opposite direction. Okay. Now, this is also the idea behind a gun and bullets. Like, the force of the gun on the bullet is equal and opposite to the force of the bullet on the gun. So as much as that gun pushes the bullet out of the chamber, the bullet pushes back on the gun, and that's why we get some recoil there. But we also recognize that the acceleration of that bullet is far greater than the acceleration of the gun, right? And so just a reminder on that. The mass of the gun is far greater than the mass of the bullet, and so because of that, the gun experiences way less acceleration and the bullet experiences way more acceleration, even though those forces are the same. They're equal and opposite in direction. Okay, so that's what's happening there. You can say the acceleration of the recoiling rifle, well, it's smaller than the acceleration of the bullet because of its larger mass. So the force of the bullet on the gun is equal to the force of the gun on the bullet, but the acceleration of the gun is far smaller than the acceleration of the bullet because it has so much more mass. Okay. You push against a brick wall with 12 newtons. Your mass is 120 kilograms, and the mass of the brick wall is 12,000 kilograms. With how much force does the brick wall push back against you? Okay. So here's the free body diagram for you. Here's the diagram for the wall. We have gravity and normal force with the floor, but we're not going to worry about that right now. We're going to focus on this idea of we have the force of the wall on you, right? And then we have this equal, sorry, this would be going the other way, right? So let's change this around. Let's say this is going to be the wall. It's going to be, okay, so we have the force of you pushing against the wall. Okay, you're pushing against the wall, but then we also have an equal and opposite force of the wall pushing against you, okay? Now, if we're talking about forces, we know that this force is 12 newtons, and so with how much force does the brick wall push against you? 12 newtons. Since we have the mass, we can figure out the acceleration, but that's not what the question asks. It asks, what was the force? And the force is 12 newtons. Okay. When a softball with a mass of 0.18 kilograms is dropped, its acceleration towards Earth is equal to g, the acceleration due to gravity. What is the force on Earth due to the ball, and what is the Earth's resulting acceleration if the Earth has this mass? Okay. So we have a softball, and then we have our massive Earth, right? And so we're going to draw two free body diagrams. Here is a free body diagram of the softball, and then here's it of the Earth. So we have the force due to gravity, or the force of the Earth on the softball. And then we're going to have an equal and opposite force of the softball on the Earth. Okay, so those are our interaction pairs there. So the first thing, what is the force of the Earth do to the ball? Meaning, what is the force of gravity, right? And we learned, I think it's the learning target just previous to this. Force of gravity, or the force of Earth on the softball, is just equal to the mass of the softball multiplied by the acceleration due to gravity. Okay, so that would be the force of Earth on the softball. Well, we have 0.18 kilograms. So 0.18 kilograms multiplied by the acceleration, 9.81. And so we have 2 sig figs, so 8 newtons. That is how much force the Earth is pulling that ball down, right? And then we have, what is the Earth's resulting acceleration? Okay, well, here, sum of the forces is equal to mass of the Earth multiplied by the acceleration of the Earth, right? And the only force in this situation acting on the Earth is the force of the softball on the Earth. Mass of the Earth multiplied by acceleration of the Earth. We know that this force is equal to that. So we have 1.8 newtons is going to equal the mass of the Earth, 6.0 times by 10 to the 24 kilograms multiplied by the acceleration. So we'll divide that over. We're saying that the acceleration of the Earth is equal to 1.8 newtons divided by 6.0 times by 10 to the 24 kilograms. Okay. When you plug this in your calculator, make sure you're putting that in parentheses or your calculator won't read that the right way. Okay. So I'm going to take 1.8 and I'm going to divide that, put it in parentheses, 6.0 times by 10 to the 24th. So our acceleration, 2 sig figs, let's see, it's that, yeah, so it is a 3.0 times by 10 to the negative 25 meters per second squared. Think of how absolutely tiny that number is. The acceleration is so small because the Earth is so massive. Okay. 6. Okay, block A rests on top of block B, which rests on the table as shown below. Construct a free body diagram for each and determine the interaction force pairs. Okay, we'll start with that. So we have A, and then we have B, and then what are they calling? Rest on a table, so maybe then we'll say table. Okay. And really you should throw Earth in there too. How about we change this a little bit? So instead of them resting on a table, we'll say that they're like resting on Earth. Okay. So we have the force of gravity, or the force of Earth on A. So that must mean we also have the force of A on Earth, okay? And then we have the force of B pushing up on A, right? That like surface normal force. Okay, so the force of B on A, which also means that we have the force of A on B. Okay. Now B, we have A pushing down on it, and then we have the force due to gravity, so that would be the force of Earth on B. Okay. Actually, it's making me want to come back here. We're going to keep this Earth. We're going to keep that one, but we're going to throw in the table again. It's going to be part of our system here, so we can recognize that difference. Okay, so now we have A pushing down on B, and then we also have B being pulled down towards the Earth, and then we have this normal force of the table pushing back up on B. Force of the table on B, which is going to be equal and opposite to the force of B on the table. Okay? Now, these are all stationary. The sum of the forces in each of these, now A and B are a system though. We're not finding the other action reactions. So we do have the force of Earth on B. We also have the force of B on the Earth. Start recognizing these. Let's see. Here's dash line. Here's that one. And then we have this one. And then we have force of the table. That one. I think ideally these don't cross. Oh well. And then we have that one, right? It's a little messy. So now when I look at this, that would be my interaction force pairs, right? Everything has a pair. What do we have next? If block A has a mass of 3 kilograms and block B has a mass of 3.5 kilograms, what is the force exerted by block B on block A? So what is the force exerted by block B on block A? So that's what we're looking for right there. Okay? All right. So let's just focus on this free body diagram for the moment. We know block A is not moving, so the sum of the forces has to equal 0. The sum of the forces are also the force of B on A minus the force of Earth on A, okay? And that's going to equal 0. So we could say that the force of B on A is equal to the force of Earth on A. And again, that's just gravity, right? And so that equation, force of gravity, is mass of the object times by acceleration due to gravity. So this would be mass of object A multiplied by the acceleration due to gravity, 9.81 meters per second squared. Okay? So that would mean force of B on A is equal to the mass of A, which was 3 kilograms. Okay, so 3 kilograms multiplied by 9.81. And then let's see, that was 2 sig big, so that'll be 29 newtons.